Hi, my name is Carolina and I'm a PhD student in the Cali group. My work is focused on finite element modeling of protection and degradation mechanisms of corrosion protective coatings used in the aerospace industry. By simulating these mechanisms, it's possible to assess very effectively a large number of variables that influence the performance and the service life of these coatings. This helps the design of new coating systems that replace the toxic chromic-based coatings used in aircrafts.
Hello, my name is Rebecca Skelton-Marshall, and I am a PhD student in Professor Rob Kelly's lab at the University of Virginia. Some of the research that I conduct here uses finite element analysis in order to determine the galvanic interactions between some dissimilar metals. The advantage of using finite element analysis softwares allows you to explore a large area of perimeter space which may not be available using experiments alone. In this situation here, we have a stainless steel fastener inserted in an aluminum panel, and we are able to use finite element analysis in order to change the scribe length along the aluminum panel to see how the galvanic interactions change. We can see that the false color plot denotes current density, and that changes along the different distributions of the scribe length.
Hello, my name is Duane Macatangay, and I'm a fourth-year graduate student at the University of Virginia, and I work for Professor Robert Kelly. So my research is on the corrosion properties of additively manufactured stainless steel. Recently, we put a lot of emphasis in the study of additive manufacturing in the department, and I've been looking at localized corrosion phenomena in these 3D printed stainless steels. We also have work on hydrogen embrittlement and the stress corrosion cracking and the corrosion fatigue of these alloys. On the side, I am a volunteer firefighter and an EMT, and I absolutely enjoy my time here at the University of Virginia. I went here for undergrad, so I've been here since 2013.
Hi, my name is Pedro, and I am a PhD student in the Cali group. In my research, I worked with the corrosion of nickel-based alloys in organic solvent solutions used in the chemical and pharmaceutical industries. I like this project because it allows me to learn a lot of new concepts in chemistry and electrochemistry, and also new techniques that I'll be able to use in my career in the future.
Hi, my name is Danyil. I'm originally from Ukraine. I'm a research associate at the University of Virginia, and today I'm going to invite you to my electrochemical and microscopic life of atmospheric corrosion. As you may know, there are existing scientific approaches to study corrosion resistance of metal or alloys using standard electrochemical measurements, where we use standard 3-electrode liquid cells like this. After the electrochemical experiments, we often bring our samples to microscopic lab for studying localized corrosion damages. Both methods work well. However, working with standard electrochemical measurements in microscopes separately, we have a gap in information of what exactly visually happens with metal surfaces during corrosion at micro or even nanoscales. Therefore, scientists decided to find a way of how to combine standard electrochemical techniques and microscope together to monitor the surface change while measuring electrochemical parameters in real time. For this, they minimized size of this to this and integrated the electrochemical cell into a transmission electron microscope. We get a so-called in situ measurements, which means measurements conducted in place. Simply said, instead of static images of the metal surfaces taken before and after corrosion experiments, we obtain a real-time video of corrosion happening on the surface of metals. And now, let's move from my home office to the microscopic lab and see what is that transmission electron microscope and how it looks like. We are in the transmission microscope lab to take images or video of the metal surface at high resolution at micro or nanoscale, the electron gun located at the top of the microscope must emit electrons down to the microscope. The emitted electrons from the top of the microscope transit our metallic sample, that is in the liquid, give us a two-dimensional image of density distribution of transmitted electron beam. Meanwhile, our tiny sample remains in liquid in the electrochemical cell, where we measure standard electrochemical signals using potentiostat like this. And yes, inside this tiny cell, we still have working electrode, reference electrode, and counter electrode. Sounds like a miracle? No, it's just scientific reality of working with in situ TEM corrosion research. Let's get back to my home office. Okay, together with you, we already saw the transmission electron microscope and the electrochemical liquid cell integrated into this microscope. Working with this electrochemical in situ TEM technique for stainless steel exposed to the aqueous solution containing sodium chloride, for example, we can capture the steps of microscale hydrogen bubble evolution, including its nucleation, growth, and release, which identifies a cathodic reaction within a corrosion damage. Also, we can couple the oxidation reduction reactions observed by in situ TEM with the change in the electrochemical potential measured during the initiation of the corrosion damage. So, I have presented you just a small part of the huge ability of the integrated electrochemical cells into the transmission electron microscope that can be applied for studying corrosion of metals. Thank you so much. Bye-bye.